Hi everyone, my name is Maxime Chagnot. I'm a CATIA consultant working for Pawl Technology in Norway. Today we'll perform a live demonstration of the 3DExperience release 21x, and we will continue our series of Introduction to Dynamic Simulation. This one will be part number 4, and today's topic would be spring. And for simulating a spring, I decided to select this example. It's a ratchet wheel. So if you turn in one direction, the wheel can turn, but in the other direction, it will be blocked by the pole. And we will add a tiny spring here between the pole and the fixed part, and we will simulate the wheel turning. Okay, so what do we have here? We have an assembly of 3 parts, a fix, as you can see the gray one, we have the ratchet wheel and the pole. There is no engineering connection, so we have to start by creating them. And as you know, I will just go to engineering connection here and always select the fix first. So click on the fix and I have a fixed connection created here. Now you can always hide the other part if you feel more comfortable doing that. I will add revolute between the wheel and the fix. So you can hide this one for the moment. We select this axle here, axis. Okay, I will show the ratchet wheel and I will select it here. Okay, we have axis, that's good. Now we select the face here and the face here. Okay, we got a revolute now, but we are going to control this angle because we need that. So you select angle here. Okay, and we will select the plane. So XY plane with the XY plane of the wheel. Remember to select control if you want to make it as an engine later, as a motor. So click on OK. No clash, no need. Okay, and now we have our revolute that is controlled. Good, and now we need to do the same with the pole. So I will just hide the ratchet wheel. Okay. We can select this axis here and this axis there. Great, and we will select this face here and this face there. Here we don't really need to create a control revolute because it's this one that will be the engine only. That's good, and you will see also that we will have a clash because this part here has a small pin that goes inside the fix, but it's no problem, we will look at it later. So I click on OK, it says there is a clash, OK, and we can hide this one again. And now we have created the engineering connection, but we need to switch to mechanism system design. Okay, so you can just search for it. Okay. And we will add a contact between the pole and the wheel, and we will also add the axial spring. So first of all, the contact. We will select group 1 would be the ratchet wheel, okay, and group 2 would be the pole. Okay, now we have, as you know, we have 2 parameters to look at, the restitution collision and the friction. Okay, if we look at restitution, the best would be to have 0. So we can actually just put 0 indeed. You can put 0.05. It will not change that much, but if you put 1, it will be a lot of bounce between the pole and the wheel, and it will not work later in the scenario. So I know I will just put 0 as restitution coefficient. Same for surface contact model. In the friction, if you have something close to 1, it will be very sticky, like it's almost like rubber on steel, for example. So it's not going to work, it's going to be too high. So here as well, I will put 0. Of course, we could put 0.1, 0.2, but closer to 1 will not work either. So here we are good for the contact, okay, and we will finish by the axial spring. And for the spring, it's pretty simple. You have just to select 2 points. So here we already have them. If you don't know how I made it, it's just a point that I created directly in the part level. So I just made a point to the circle, in the middle of the circle of this pin, and the same here. So you select this one and this one. two entity, great, force, etc. And here you have to put a value. And the value, it took me a bit of while to understand how it works. But if you, here it's kilogram per second, square second. So there is one unit missing, is actually the length, if you want to have the coefficient for a spring. And you will have it here. Normally, you will see we want extension, or we can actually take bidirectional in that case. It's no problem. It will normally find it. So if we take 50 just to see, okay, I will just edit it again. Not this one here. And the value here has been created. So we have 13 millimeter between these 2 points. So basically, if you take this value and you multiply with that in meter, you should arrive around 0.6 Newton. So that should be about half a kilo. So that should be quite enough for our spring here. We can, of course, always play. We can put less, indeed. We can put a lot more. If you put 1000, it will never work because you will have too much force from the pole to the wheel, and the wheel will not turn. So I've already done some tests. 50 is a good example. I recommend you to try different value, of course. And now what we have to do is to create the mechanism. So we can update. Okay, here we have all the engineering connection we need. We create a mechanism. So mechanism ratchet wheel, for example. Okay, it will be here under the product, and we can always have a quick look at the mechanism manager. As you can see, there is the revolute we can control because there is an angle, and this one is not drivable because it's not controlled. So actually it's pretty great. It's no issue that we are not fulfilling the degrees of freedom because we are not in kinematic simulation, we are in dynamic simulation, so obviously we can have degrees of freedom. Okay, quick update again. That's great. Now we have to switch to mechanism system experience to run the dynamic simulation. Okay, remember not having this option here. We will create our dynamic scenario. So I will call it Ratchet Wheel Simulation. Here it is. Okay, what do we need now? Of course, we will need a dynamic scenario, but first we need some excitation, and we will use the velocity motor excitation. So here, basically, we will need a support, and the support will be the command here, the revolute. And we can put also some value, 50 turn per minute. Okay. I realized I forgot to do something. And in mechanism system design, I forget to control the weight. And that's something you should always do. What I did this time is, instead of having the density of steel, I already put a material with a density in it on each part. So now, when we do the weight, we will verify that everything is green. You see, everything is computed, so we can just make it sure again. Click this hyperlink to verify, update. Okay, and now we have the full weight of everything is bad still. Okay, now we have the weight, so that's good. I go back to my simulation, and in that case, I decided not to select the gravity because it's not really the case that interests us here. Plus, it's not big amount of weight, so I don't think it will be a big impact on the simulation. I would focus more on the spring only. So just velocity motor excitation, and basically this wheel will turn. We can do the dynamic simulation. We select the velocity as the excitation. Remember to, when you do a simulation, you select something small because it can take a bit of time. So we will select also Simpletic Euler. Okay, we should be good so far. We do the simulation, it's turning. Great, quite fast, but it's turning. That's not bad. You can always replay a bit the dynamic simulation, and I can I like that I can turn when I'm playing. So in that case, it's working. Clearly, the pole is working, the spring is working as well, because it's coming back to the wheel. So we validated that part at least. Okay, so don't worry, here I do it in the opposite direction. So you see it's working pretty well. The pole is going back to the wheel. Okay, and now what I will do is, as I told you a bit before in the video, we have a tiny pin here going through the fixed part, and I don't really like that because it cannot happen in real life. Therefore, we will create a hole here, and I want this hole to have the good shape of for the pin. So what you can do here is we will create, or first I will exit the video. We can create a trace. Geometric trace. So you can just call it trace, okay, or traces, it's up to you. It will appear here directly under the result, and here it will ask us to select an element, and this one will be the point here, the point that we created here. Click on OK. It says that we will have 101 entity. It's going to make a list of points basically, and it will make the curve. So here we have the trace that appears in the different tab, but it's no problem. You can always put it back after in the assembly. The first thing I want to do is going to display app option, and I will select this point filter here and just select all the point as you can see here and click on hide and click again on point filter because we don't want this filter to be active. So you see now we have actually a list of curves. It's not only one, you have several, because as you can see in the demonstration, the simulation, the pole is going up and down. So therefore you have a lot of line on top of each other. So we will not use them, but we will use the shape. Okay, what we can do now, we have the assembly here, we have the trace, we can just do a drag and drop. You select the trace, and you drop it directly in the assembly. You can see you have a small shortcut here because it's linked to the simulation there. Okay. Now what I will do is I will not work with the trace, I will work with the fixed part. I will just double click on it and we will switch to Pawl design. When you click on the 3D shape, you switch to Pawl design. Great, and I will just create a sketch. And as you can see here, you have a nice feature called cylindrical elongated hole, and we will select this one. And you see you are going to make a diameter with that. So clearly it's a bit big now, and obviously something is a bit sketchy here. I will not use parameter in that case. I will use the fix option here. So, well, this is not perfect because we cannot, this design is not parametric. But in that case here, it's working pretty well because we are using the traces, so it will be hard to get something parametric anyway. Another thing, the radius of my pin is about 1 millimeter, so I will put 1.2. Okay, we have a bit of tolerance in that way. You see I fixed my point here. We know that this is the lowest area for our pole. And here we can just control that and put it a bit over. You see, I can make it here, but I will make it a bit over. As you can see, we have about 1 millimeter over maybe. That should be good for me. I'm not even going to control my radius. It's no point. I can just control it manually. It's working well for me, and you can fix that. Okay, we can even fix the point. Here it's fixed, and we can just exit the sketch and make a pocket out of that sketch up to next. And now it's perfect. We have the perfect hole for our pole. And I can just hide this trace now. I don't need it anymore. Okay, great. We can go back to, of course, we can always make a quick update because now you make a hole in the, we make a pocket in the fix, so kind of always nice to do a small update and also verify that the weight also normally has changed a bit. Okay, not that much, but change a bit. So it's better to do it anyway. Now everything is up to date, that's great. And we can go back to the Ratchet Wheel simulation. And this time I will change a bit. The scenario, I will remove the velocity motor excitation because the wheel was only turning in one direction. I will switch it to a position motor. You will see here, I just double click on the scenario, and here I will select position motor excitation. And same here, I will select the command here. And here you have several options. Distance oscillating, we will select oscillating because we want that our wheel will turn in that one direction and turn in the opposite direction. I put 1 Hertz and I will put 90 degrees. So we can see now it will turn in one direction and turn in the other. Do a small update and be careful now because you have a scenario with 2 excitation and it will not work. You have to select one of them. We want to remove the velocity of the equation because we don't want the wheel turning in one direction. So we will only use the position motor excitation. Be sure that it's 1 second also. Okay, and now we can just turn. And you see here, it's working perfectly. We validated that our pole is working. The spring is the good strength for this pole. So now I can recommend you to play a bit with this spring, change the value. You can put 0. You will see that if it's 0, then the spring will probably go away and come back, and that will not be good. And same for the, if it's too high the value, it will not work neither, because then the wheel will not turn. Okay, it seems here we have a bit of penetration inside the wheel. Okay, so here I think we can see a problem here. As you can see, it's working, and when it contacts again, then the pole is messing. It's actually going inside the wheel, and that's not good. So we can see again a bit faster maybe. You see it's coming back here. And it's going inside. And I think the reason why it could be that the spring I selected is actually bidirectional, and we don't really need that. We could just need extension spring. So we can see if I can modify that. Here I will go to the spring, axial spring, and this one I will select just extension only. Update, go back to my simulation. We want to make an update also here. Position motor, I think it's pretty good, the motor I have. 1 second, Simpletic Euler. Okay, let's try again. Here it's doing it again. Then that could be linked to maybe our scenario. Here there is some penetration max. What if we put this to a bit lower? I have no idea if it will change something. And if we do the opposite, okay, I think that could have helped actually. I understand now what I control the penetration max, and actually it will impact directly on the tessellation of the shape we have here. So you see, I think our penetration was a bit too low, and when the pole is going, you will see we can play a bit with the scenario again. I will show you. I think I understand why. What was the problem? I go back to 0.2 maybe. Okay, let's zoom a bit more here. You see here, the dynamic simulation is actually using the surface of the model to compute the dynamic simulation. And as you can see a bit here, the top of our wheel here is going a bit inside the Pawl, and that's how the dynamic simulation is done. I think it's the tolerance in the software for making this simulation a bit easier. So you can play a bit with the penetration max to, I guess, put this tolerance to a bit higher. And as you can see now, it's going a bit inside, but I think it's the best for the simulation. It's a bit simpler for the software maybe to calculate. Okay, but at least now we know what it's meant for, and I recommend you to play again this scenario. I think it's really nice. Play again with the Axial Spring, change the value, maybe put 1000 just to see that it will probably not work. You can also play with the parameter of the contact, restitution and friction. It will give you different results. And as a tips I give, I will recommend to use 1 second for the simulation for you to not have like very long time of calculation. If you put 10 seconds, the computer will maybe calculate for the whole time and can take a bit more time. So not always easy. Thank you very much for watching this video. I hope you like and enjoyed our tutorial about 3DExperience. Do not hesitate to visit our website www.pawltechnology.com, and please share, subscribe, like and comment the video. We are very happy of all your comments so far, so thank you very much. Have a nice day, stay home, goodbye.